Hello students, welcome to the physics session. We will be discussing system of particles in this session. Okay. Um,
Right, okay. So we have one last concept left over for the portion, right? Tomorrow's exam. That is system of particles. System of particles. System of particles and rotational motion also can call this. System of particles and rotational motion. It is one of the very important chapters. And in this, let us see what are the concepts we have to look into briefly. First, we discuss briefly about center of mass. Center of mass. Under this, we will see what is center of mass and how to calculate center of mass of discrete particle system and continuous mass bodies. For discrete particles and for continuous mass systems. And also under this we will discuss about how to calculate the parameters related to motion of center of mass. Motion of center of mass. Motion of center of mass we will denote in short with the CM. Some books will give you COM, center of mass or center of mass. Center of mass. Okay. Motion of center of mass. As part of this, we will discuss about when a body is moving, its center of mass also will be moving. So that body will be velocity, acceleration, momentum, etc. And then we will discuss briefly about some rotational parameters. Before that, even you need to have an idea about cross product of vectors. Because to understand one of the rotational, usually the rotational parameters, we need to have an idea about what is the cross product and how to express the cross product and how to find the cross product between any two vectors. We'll see briefly about this. Then we'll discuss about rotational variables. Rotational variables. Like already in motion plane we have discussed what is angular displacement, angular velocity and angular acceleration. Right? Those we have to recollect back, and in addition to those, rotational force called torque. Rotational force called torque and rotational momentum called angular momentum. And what are the relation between these rotational variables and linear variables? These parameters we will see briefly here. And rotational variables and law of conservation of angular momentum L. Then we will discuss briefly about moment of inertia. Moment of inertia is denoted by I. Then here we will discuss briefly about how to find moment of inertia of discrete particles and continuous mass bodies. Discrete particles and continuous mass bodies. Under this only, to find the moment of inertia, especially of continuous mass bodies, we will discuss about so here for discrete particles and continuous mass bodies. While discussing about continuous mass bodies, we will use two theorems. One is parallel axis theorem and another is perpendicular axis theorem. So what are those? We will see briefly. Then at the end we will discuss briefly about rolling motion. Rolling motion. Briefly. Right? So let us see one by one. First, what is center of mass and how to calculate center of mass of a system. So write down some heading. Center of mass. So what is this center of mass? So in this space only have to discuss Just keep this aside. What is the center of mass? Center of mass in any system is a point where the entire mass is supposed to be concentrated or assumed to be concentrated. It is called center of mass. So if you want, you can write the definition. What is that? A point where the entire mass of the system, a point where the entire mass of the system is supposed to be concentrated. Is supposed to be concentrated. Is called center of mass. Okay. The point where the entire mass of the system is supposed to be concentrated. Supposed to be means assumed to be, but not actually. Okay. So here you have to write a note. Center of mass need not to be within the matter, within the material portion, or need not to be within the matter. It may be outside the matter also. It may be outside the material portion also. So for example, if we have, we'll see this later, but for understanding purpose here, if we have a ring, this is a thin ring. Okay? Thin ring, center O and radius R, center of mass will be at the center, geometric center, but here no mass will be there. For a disc also will be at the center only, but in case of a disc, it will be at the center where some part of the mass will be there, but here nothing will be there. It is a hollow space. There center of mass will be lying. So from this you can understand that center of mass need not to be at a point where mass is to be present. Okay? So that's what you can understand. Even for horseshoe magnet or kind of U-shaped objects, center of mass will be somewhere in the space where material part or matter is not supposed to be there. There center of mass will be get. Okay? So these based on these examples, you can say that center of mass need not to be located within the matter. Need not to be located within the matter. It can be outside the matter also. Center of mass need not to be within the matter. Okay? Right. Let us see briefly how to find the center of mass of discrete particles. Center of mass of discrete particles. Say for example, if you have a two-particle system, two discrete particles are there, two particles M1 and M2, which are separated by some distance, but here M1 is at a distance of, if they are lying only, let us say, on x-axis, and they are lying on x-axis, and this is, let us say, this is a reference point or origin. From the origin or reference point, if M1 is at a distance of x1 and M2 is at a distance of x2, then center of mass will be for these two particles will lies on the line joining the centers of the masses, and here between these masses, and if this position is given by, you can say xcm, because it is lying only on x-axis. So the center of mass will also lie on the same line, that is x-axis. So xcm is equal to m1 x1 plus m2 x2 divided by total mass m1 plus m2. Right? Got it? Whereas if the particles are located in a plane, xy plane, like something like this. Here M1 is there. Its coordinates are nothing but x1, y1. Right? And there is another mass M2. Its coordinates are x2, y2. Then the center of mass of these two particles may lie along the line joining the centers somewhere in the space. If this is origin, this is x-axis, this is y-axis. Somewhere here it may be the center of mass. So position of center of mass will have two coordinates. So if here you can write here the coordinates may be given. Sometimes position vector also may be given. Position vector of these two particles also may be given, R1 vector and R2 vector. So in either way, we can have to write the expression for center of mass. If position vectors are given, we have to find xcm, then ycm, then this will be the position vector of center of mass, rcm vector. Its coordinates are given as xcm, ycm. Got it? So you can say rcm can be expressed as xcm I cap plus ycm j cap. where XCM is equal to m1x1 plus m2x2 by total mass. If in case of two particles, so when particles are there, m1x1 plus m2x2 plus so on plus mnxn you have to take. So m1 plus m2 plus so on plus mn, the total mass you have to take. So and YCM, where YCM is equal to m1 y1 plus m2 y2 by total mass, m1 plus m2. So this is how you can take it. Right, this is RCM. If coordinates are given, otherwise, you can also write the RCM is equal to, in terms of vectors also given, m1 r1 vector plus m2 r2 vector by m1 plus m2 also can take. Okay, in terms of vector. Okay, this is XCM I cap J cap rotations are used otherwise in this case also. So if vectors the coordinates of the particles are given, you have to find out this XCM ICM and then you can write the position vector of center of mass. Directly the coordinates of these are given, then you can write that is position vector also. So vice versa. Is it clear everyone? Right. This is briefly about how to find the position. What you call the position of center of mass in case of two particle system. If you have n particle system, you can generalize this. Again, no need to write here, but try to remember. You can generalize this to n number of particles. If the particles are in space instead of a plane, if the particles are in space, so that it will have three coordinates: x1, y1, z1, x2, y2, z2. Then zcm also will come here plus zcm k cap will come in space if the system is in space. Got it? Two particle system or n particle system. So by making use of this points, you can calculate this. This is briefly about how to find the center of mass of discrete particle system. Whereas if we have a continuous mass distributed system, write down next point. Center of mass of copying simultaneously. I have to copy quickly along with me. So if this diagram is clear, of course you can write as this is RCM vector is equal to XCM I cap plus YCM J cap. XCM and YCM you can write. Right? Can I erase? Next, center of mass of continuous mass distributed systems. So here, as we have considered two masses which are in distances of x1, x2 from origin, we have taken m1, x1 plus m2, x2 by total mass. But if one of the particles is at origin, if m1 is at origin, x1 will be 0. So, center of mass XCM can be taken as 0 plus m2 x2 by total mass you can take. This kind of questions usually will ask sometimes. Okay, you have to remember that. So next, center of mass of continuous mass distribution systems or continuous mass distributed systems. In such case, how to find? So if you have, say for example, you have a rod of length L and a mass M. Mass is distributed in this continuously. Obviously, center of mass of this will be is geometric center. But to calculate this, you have to use, if it is having only one dimension, very thin rod. So if this is the origin and it is lying on this x-axis, so that its length is L. Then you have to use a relation to find XCM is equal to integral of x dm by integral of dm. Integral of dm will give you total mass. Here, because it is lying on x-axis, you have to take x dm. If it is lying on y-axis, y dm you have to take. If it is in general, in space, if you want to take, so same way of representation you have to take. Okay? So even RCM you can take. If its center of mass is supposed to be lying in space like that. So it is the expression for this is how we can use the expression we have used to calculate the center of mass of continuous mass distributed systems. Then this is briefly, that's it. But you have to remember that for a few systems, that is a regular shaped bodies. For regular shaped bodies. For regular shaped bodies. Center of mass lies at its geometric center. Geometric center. What is this geometric center? Let us see some examples. First thing, if you have a disc. So if you draw one diameter, another diameter, the point of intersection is nothing but geometric center. Point of intersection of the diameters gives you geometric center. There center of mass lies. If it is uniformly uniform distributed. Whereas if you have a square shaped sheet or lamina, so here also if you draw a diagonal, another diagonal, the point of intersection of the diagonals gives center or center of mass. We call it a geometric center. If you have a ring, even in case of a ring also, if it is a disc, if you have a ring, so even though here for a ring, inside there is no mass, but if you draw a diameter and a diameter, the point of intersection gives the position of center of mass. But even though there is no mass is concentrating over there, right? Whereas if you have a sphere, solid sphere or hollow sphere, whatever it is, center of mass will be at the point of intersection of the diameters only here also, in case of sphere. Instead of square, if you have a rectangular sheet, for that also, at the point of intersection, the diagonals only, the center of mass lies. Got it? So, you have to remember the positions of center of mass of different objects, continuous mass distributed systems here. Next, we will see briefly about, this is about what you call center of mass and center of mass of discrete particle systems and some continuous mass distributed systems. Next, motion of center of mass. Find out next, motion of center of mass. Yes, can I erase this? Everyone? Motion of center of mass. Motion of center of mass. Motion of center of mass. Right. So if a system of n particles, discrete particles, or a continuous mass body like a ring or a disc, if it is moving, or if you have a block, if it is a solid block, cubical block, so its center of mass will be at the point of intersection of the what is called body diagonals for the cube. So if it is moving, it is sliding. Okay, if it is sliding, every particle will be moving with the velocities, the particular velocity. In case of the solid objects, or we call it as the rigid bodies. So center of mass will be here. Center of mass will be moving with the velocity called VCR. It means with the time, the rate, if the position of center of mass is changing with respect to its surroundings and also the time, then it is center of mass is said to be in motion. If it is in motion, then the velocity of center of mass is given. Actually, if your system is made of different particles, discrete particles also. System can be made of discrete particles also. So for example, if you have like same two particle system, if two particles M1 and M2 are there, following everyone? So if the center of mass is lying somewhere here, center of mass, so it's what, this is origin, this is x1, this is x2, and position of center of mass is xcm. If the two particles is forming a system, if it is moving, means position of this particle should change, then position of center of mass will change. But the change in position of center of mass with time gives velocity to it. So that can be expressed as position of center of mass is given as m1 x1 plus m2 x2 by m1 plus m2. Velocity of center of mass is nothing but, you can write this as velocity of center of mass is equal to d by dt of xcm. It is the rate of change of position of center of mass. So this can be further expressed as m1 into d by dt of x1 plus d by dt of x2 by m1 plus m2. The d by dt of x1 will give you velocity of the first particle, d by dt of x2 gives velocity of second particle. So simply you can write it as m1 v1 plus m2 v2 by total mass. In vector form if you want, here you can write this in vector form, m1 v1 vector plus m2 v2 vector by total mass. This gives velocity of center of mass. Similarly, if the particle is moving, the system is moving under some external effort, so that the entire system is moving with some acceleration, then acceleration of center of mass can be expressed as d by dt of velocity of center of mass. So you can write directly, it is d by dt of v1 by v1 is nothing but a1. So you can write it as m1 a1 vector plus m2 a2 vector by total mass m1 plus m2. Is it clear? So from these expressions itself, we can write a few more variables, parameters related to the motion of center of mass. That is, if the center of mass is moving, system is moving, center of mass is moving with this velocity, we can say center of mass is moving with some momentum also. So momentum of center of mass is given by PCM is equal to momentum of center of mass is equal to simply the vectors what? Momentum of every individual particle, P1. So here you can, what you can write this from this itself. If you multiply this here, total mass into VCM gives PCM is equal to m1 v1 is nothing but p1 vector plus m2 v2 is p2 vector plus so on plus pn for n number of particles you can write. So in this way you can write momentum of center of mass. Momentum of center of mass is equal to vector sum of the moment of individual particles. Vector sum of moment of individual particles. Likewise, from this, you can write when a system is moving with some acceleration, means some force is acting on that, external force. So, force acting on center of mass can be expressed as m1 plus m2 into ACM. That is nothing but force acting on center of mass is equal to what? Force on first particle plus force on second particle plus so on plus force on the nth particle. So, if n forces acts at different points, the vector sum of all those points is equal to net force acting on center of mass. So based on these relations, direct numericals also sometimes they come across. Just you need to have an idea about these expressions so that you can attempt those. This is briefly, these are a few points related to motion of center of mass. Motion of center of mass. Right? Now let us see what is this cross product and how we are going to use in understanding these rotational variables. Write down next cross product. Have you copied this? Everyone? Can I erase? Cross product of vectors. Cross product is also called as vector product. Vector product. Vector product. So, vector product. Especially we have already studied briefly about this in vectors. Multiplication, we have discussed about addition of vectors, subtraction of vectors, multiplication of vectors. So vectors can be multiplied in two different ways. The multiplication of vectors as a classified into two types based on the resultant parameter. If you multiply two vectors, if the resultant is also a vector, we call such product is a vector product or cross product. If multiplication of two vectors result in a scalar, we call such product is dot product or scalar product. So here we are dealing with, especially in case of rotational motion, we will be dealing with cross product of vectors. That's why we need to have an idea about this. Say in general, you can write A vector cross B vector is the representation of cross product of two vectors. It can be expressed as is equal to A B sin theta into n cap. So where A is magnitude of A vector, B is magnitude of B vector, and theta is angle between these two vectors, and n cap is normal, unit normal, which is perpendicular to both A vector, B vector, and to the plane containing both of these vectors also. So this is called as a resultant vector. The resultant vector will be perpendicular to both A, B, and also to the plane containing A. That is the meaning of it. Okay. So how we are going to use this, we'll understand here. And before that, so let us also understand that if you are dealing with, if magnitude of the vectors and angle between them are given, directly you can use this expression to find the cross product between two vectors. Whereas if the vectors are given in components form, so that means like AXA vector equal to AXI plus AYJ plus AZK. B vector is given as BXI plus BYJ plus BZK. Then A vector cross B vector is given by A vector cross B vector is can be calculated by using what method? Determinant method. What method? Determinant method. In this you have to take I, J case and the components of A, AX, AY, AZ and components of B, BX, BY, BZ and I hope you remember this how to do it. Then it is equal to I cap into, you have to take the cross product, what do you call it? Diagonal products of these elements. So AY, BZ, AY, BZ minus AZ, BY. Right? This is I component. J component, for J component I have to take negative sign. So here we can write minus J cap into, you have to close this column, then you have to take the product of this AX, BZ, AX, BZ minus what is that? AZ, BX, AZ, BX. Then plus K cap into, K cap means you have to close this column, product of this. First you have to take what is this? This diagonal, product of this diagonal elements minus this diagonal elements. You can take left diagonal or right diagonal, whatever the name you can give. So AX, BY, K cap into AX, BY minus AY, BX. This gives you what? I, J, K components of the resultant vector. So I cap with the positive sign, J cap with the negative sign I have to take. And K cap with positive sign. Okay. So this is briefly of how to find the vector product of two vectors. Usually based on these two formulae only, we deal with the what do you call the questions. Sometimes the two vectors will be given. You will be asked to find the angle between them. Angle between them. So once the vectors are given, you can see from this. Actually here, this gives you the magnitude of the resultant vector. Magnitude of resultant vector. You can call this as some C vector also. Magnitude of C vector is this part. This gives the direction. So you can also write from this A vector cross B vector is equal to that, where magnitude of this is equal to AB sin theta. Magnitude of that. Okay. So from this you can say angle theta is equal to, or sin theta is equal to this by this. If you are asked to find the angle between them, you can use this relation. Sin theta equal to this, or theta is equal to modulus of A cross B by AB. Sin inverse of, or simply you can say sin theta is equal to this. This gives the angle between the two vectors. Got it? So these are few points you have to remember about the cross product of vectors. Now we will try to recollect back the rotational variables and law of conservation of angular momentum. Rotational variables. What rotational variables you have to keep in mind here while dealing with what you call rotational motion? Because we are dealing with rotational motion, right? So write down next subheading. Next subheading: rotational variables. Rotational variables. Law of conservation of angular momentum you can take later. First, rotational variables. Yes, copy this. Can I erase? Yes, everyone? Rotational variables. Yes, rotational variables. So already I have discussed about rotational variables like angular displacement theta. Yes, do you remember? So what is the expression for theta angle? When a particle usually can be taken, this the definition of this mathematical expression for this is defined by using circular motion, right? Uniform circular motion. According to that, angular displacement is equal to arc by radius. Angle equal to arc by radius. Arc you can take it as S and radius R. The particle is moving on a circle. What is that? So this is the center. Radius. If the particle is moving from somewhere here from P to q here, so that the radius vector is going through small angle theta. It is moving from here to here. This is linear displacement. This is angular displacement. Right? The angle swept by the radius vector. The angle swept by the radius vector when a particle moves from one point to another on the circumference is called angular displacement. It is given by this. So this is also called an angle relation between angular displacement and linear displacement. Or you can also write it as S is equal to R theta. This implies S is equal to R theta also can write. S is equal to R theta. Right. From this you can also mention what is angular velocity. Angular velocity omega is given by, so if you differentiate this with respect to time, as R is constant, 1 by R into ds by dt gives you V by R. Omega is equal to V by R, or you can write V is equal to R omega. And here, next another angular variable is angular acceleration. What is that? Alpha is equal to, if you differentiate this again, 1 by R into A, so you can write it as A by R. This can also be expressed as A is equal to R alpha. A is equal to R alpha. Is it clear, everyone? Okay, this is fine, but while these relations you can write in vector notation. While writing vector notations, you have to be a little bit careful. Say for example, this you want to write angular at a given point, the tangent gives the direction of displacement and direction of velocity and the direction of tangential acceleration. S, V and AT, or VT and AT, the tangential components. The tangent drawn at a point gives the direction of displacement and velocity and even acceleration at that point. We call it as tangential acceleration or instantaneous acceleration. So to find these relations, we have to use the cross product or right hand thumb rule. According to this, usually angular variables, all angular variables are called as axial vectors. They will be acting along the axis. So they are called as axial vectors. So theta, omega and alpha act along the axis of rotation, along the axis. For a circular path, axis will be a line passing through the center and perpendicular to the plane. So if this is theta, I will take theta. So in this, to give the direction of S, theta cross R will give you that. So in vector form, if you want to write, what is that? S vector is equal to theta vector cross R vector. Similarly, omega vector is equal to as what you can take the omega vector cross R vector from this omega vector. Take in reverse order. R omega, this for convenience we have taken that. So omega cross R, if you take, then we will get this V. So V vector is equal to omega vector cross R vector. Similarly, A vector is equal to what is this? Alpha vector cross R vector gives the vector rotation of these variables. Is it clear, everyone? So these are briefly the angular variables which we have already discussed. But in this chapter, we are going to discuss two angular variables, very important variables. Those are nothing but angular force. We call it as torque or moment of couple. Torque or moment of couple. And another one is angular momentum. Let us discuss those now. This is a recollection. We are recollecting back. Still, try to copy this, everyone. Copy it. Right. Next, write down. First parameter is torque. Torque acting on a body in rotational motion. Torque. Simply can say torque. Actually, to understand this, you have to recollect back the laws of motion, concepts in laws of motion chapter. In laws of motion chapter, we have discussed about linear momentum, then what we call Newton's second law of motion, right? From Newton's second law of motion, I have got the expression for force, right? Same parameters I have to recollect back here. Momentum is momentum is mass into velocity. Here, rotational analog parameters are to take. Similarly, their force is mass into acceleration. Here, rotational variables have to take to express the rotational force called torque. So, what you have copied? I have copied torque. So we can just go ahead with the order. First, let us take the angular momentum. Just like in laws of motion, I have discussed first momentum, then force, right? Same order. Let us take angular momentum first. Angular momentum. It is denoted by the symbol capital L. Angular momentum is denoted by the letter capital L. Okay? And there, how I have in linear motion, how I have mentioned the linear momentum? Mass into velocity. Here, the same way, express angular momentum is equal to rotational analog of mass is called moment of inertia. Moment of inertia. Then I have discussed about the parameter called inertia. That is different. It is different. There, inertia is the inability to change the state of a body in linear motion. Okay, this is also the same, but actually here the inability to change the state of a body in rotational motion. Okay, rotational inertia is referred as. So moment of inertia into as the m into v here, I into angular velocity omega. Angular velocity omega. Is it clear? So this is a vector, so its direction will be along the direction of omega. They are axial vectors, so its direction also should be along the axis of rotation. So you can write L omega, L vector is equal to I vector. L vector is equal to I vector. I into omega vector. Is it clear, everyone? The vector representation. Angular momentum. But angular momentum, just from the previous concepts, you can also write this as omega from the previous relations. Omega equal to what? V is equal to R omega. Omega equal to V by R. V by R. So from this, you can also write the different way of representation of this. Here, after discussing the concept of moment of inertia, then you can replace I is equal to mr square for a particle. If a single particle of mass m is moving with some moment of inertia, then you can write it as mr square into this is V by R. On simplifying this, what you can write it as mr square into, it is rotating about the axis whose distance from the center of mass is R, into V by R. On cancelling this, we get mvr. So angular momentum can also be expressed as mvr in terms of linear variables. In terms of angular variables, I omega. In terms of linear variables, mvr. M is linear mass, V is linear velocity, R is radius. I mean the distance of axis of rotation from the center of mass or center of gravity in colors. Okay? Right. The another here in itself we will discuss this concept of law of conservation of angular momentum. Law of conservation of angular momentum. Okay? Law of conservation of angular momentum. But actually this will be related with angular force called torque also. We'll see that relation afterwards. Just concept wise, what you can say is, it says that just like in linear motion, the net momentum of an isolated system is always remains constant. The same thing you have to take. What is that? Is L is equal to I omega is equal to constant. This is the mathematical expression for law of conservation of angular momentum. What does it mean is I1 omega 1 is equal to I2 omega 2 is equal to constant. Is equal to constant. This is the mathematical expression for law of conservation of angular momentum. Got it? One way of representation. This can be expressed in the other way also in terms of torque. How? We'll see later. So before that, let us see what is torque. What is the rotational force called a torque or moment of couple or couple. Copy this fast. So based on these, many of the times the questions are asked based on law of conservation of angular momentum. Right? So there are some applications also, just to have to remember conceptually, something like if a body is rotating, so something like this, you are stretching your hands and rotating about your thigh. So your mass is distributed throughout your hands, stretched hands, etc. So moment of inertia, as say mass of this hand will be from the axis, the center will be this point, the line passing through your center of the body. As R is more, mr square, moment of inertia will be larger. So the product to be constant, omega should be lesser. That means if you stretch your hands, you will be rotating with less speed. Whereas if you hold your hands closer to your body during the rotation, you can see, you might have seen in this in gymnastics and all, right? If you just bring the hands closer to the body, as the mass moves closer to the body, moment of inertia will reduces. To keep the momentum, what you call angular momentum constant, angular velocity will increase. That means if you bring the hands closer, or even just instead of stretching the leg, if you bring like this closer and the hands also closer, you will rotate with larger speed. Same way if you stretch, then the speed of rotation will decreases. This kind of examples you might have come across while discussing the theory part. You have to remember those conceptual points also. Okay? So this is briefly about law of conservation of angular momentum. But this you may come across during the rotation of a disk, and if you keep one mass on that, what happens if you move the mass, if you move the masses to closer points or the further points, what happens to what you call the velocities and moment of inertia, like this kind of questions will come. Right, next write down torque. Torque. It is denoted by tau. It is denoted by tau. Just like this, what is called angular momentum can be expressed in different ways. From linear motion directly you can write here, or from linear motion directly you can write as F is equal to, because F force equal to mass times acceleration, we can take this as rotational force is torque. Torque is equal to rotational analog of mass is moment of inertia. Rotational analog of acceleration is alpha. You can write tau is equal to I alpha. Can be I alpha. So its direction will be along the same direction. It is a vector. Just like F vector is equal to MA vector, this also is a vector. And the moment of inertia is a scalar. Right? Its direction will be along the F direction. That is one way of representing this. The other way, you can also write this as here alpha, you can relate with the tangential acceleration. Tangential acceleration. So in the circular motion, tangential acceleration can be expressed in terms of also there we come across two kinds of accelerations, linear accelerations. One is tangential and another is centripetal acceleration. Right? So in terms of those, you can replace this in a different way. Okay? But this further, from Newton's second law, you can also express because force is equal to dP by dt. From Newton's second law, you can express this as tau is equal to dl by dt. dt. Rate of change of angular momentum is torque. Is called torque. Is it clear, everyone? So here, based on this, you may come across one condition. That is, what is that? Same, the previous condition. What is that? Law of conservation of angular momentum. It states that the total angular momentum of a system remains constant, always constant, or provided if no external force acts on the system. If no external force acts on the system, that is, if external torque tau external is equal to 0, then you can write dl by dt is equal to 0. This implies L is equal to constant. L is nothing but I omega. I omega is equal to constant. This is another way of representing law of conservation of angular momentum. That's why I told you can write this in terms of tau. We'll see that later. This is the one. So the relation between, sometimes direct formula will be asked, which of the following gives a relation between torque and angular momentum. Torque and angular acceleration is this. Torque and angular momentum is this. Got it? Right. So, right, this is briefly about what you call torque. But torque, in different cases, can be expressed, especially when you are dealing this as a couple, a moment of couple, we express torque tau is equal to force into perpendicular distance. Force into perpendicular distance. Perpendicular distance of the line of action of the force. Force into perpendicular distance. So this also will use this formula, this formula, this formula. So depending on the question, on the data in the question, you can use any of these relations. Okay, you have to understand based on the data in the question, which relation you have to use. Okay? Right. This is another way of representing torque acting on the system. These are few rotational variables. Rotational variables. Is this clear, everyone? Here itself, you have to remember one more very important concept is equilibrium of a body. Equilibrium. In linear motion, we have discussed about equilibrium, the condition for equilibrium when linear force is acting. So we have discussed about, I hope, the condition for equilibrium of a body when two forces are acting on the body. What is the condition for equilibrium? Three forces are acting. What is the condition for equilibrium? Here, in rotational motion, what is the condition for equilibrium? In especially rotational motion. So our total for rotational equilibrium, Total equilibrium. 2 points will come across here. 3 points for that matter. For linear, when a body is said to be in total equilibrium, when the body is in linear equilibrium under linear forces and equilibrium under rotational forces, then the body is said to be in total equilibrium. That means mathematically, let us see, write down the heading, equilibrium of a body. Rotational equilibrium of a body is total equilibrium of a body. Total equilibrium. Total equilibrium of a body. Total equilibrium of a body. When a body is said to be in total equilibrium. When a body is said to be in total equilibrium. When the body is in both translational equilibrium and rotational equilibrium, then it is said to be in total equilibrium. Write down. When a body is in translational equilibrium, when a body is both in, translational equilibrium and, I am repeating, when a body is in both translational equilibrium and rotational equilibrium, then it is said to be in total equilibrium. Then it is said to be in total equilibrium. Okay? What is this translational equilibrium condition? What is the rotational equilibrium condition? You got to remember this. For a body to be in translational equilibrium, or you can write it. The condition for translational equilibrium is, the condition, write this. The condition for translational equilibrium is F net is equal to 0. The condition for translational equilibrium is F net is equal to 0. The condition for rotational equilibrium is tau net is equal to 0. Got it? Condition for translational equilibrium, net force should be 0. Condition for rotational equilibrium, net torque should be equal to 0. If the body is in both translational and rotational equilibrium, then only it is said to be in total equilibrium. If net force equal to 0 but net torque is not equal to 0, then the body is not in total equilibrium. It may be in translational equilibrium, but it is not in rotational equilibrium. That is the condition of rotation actually here, you can say. So for example, if you have, say, you have a water bottle, to open the cap, you have to apply the fingers like this, or fingers like this will open, right? While applying, you will apply one force in this direction with this finger. With this finger, same amount, even single finger you are using, same amount of force will apply in opposite direction. So equal and opposite forces will apply in opposite directions. One force in this direction, another force in this direction. About the center you can say F and here. So net force upward is equal to net force downward. So net F is equal to 0. But this will produce a torque, rotational effect. So torque is not equal to 0 in this case. So in this case, opening the mouth or the cap of a bottle is said to be in translational equilibrium, but it is not in rotational equilibrium. This is an example for that. Is it clear, everyone? So that is the meaning of it. If both are 0, then that will come across, especially in case of dipole, electric dipole. Say if we have, this is electric field, if we have minus q and plus q, following. So this is direction of electric field. Force on this will act in the direction of field, and positive charge, negative charge in opposite direction. Force on positive charge, force on negative charge. Are you following? So net force, both forces are acting on the same line. Net force is what? Equal forces. F plus F minus F is 0. So net force is 0. So the dipole in this case is said to be in translational equilibrium. And at the same time, as net force is 0, it is not producing any torque also. Because both are acting on the same line of action. Here the line of action will be different. Then only the torque will be produced. Here line of action is also same, so no torque also. So net force is 0, net torque is 0, so it is said to be in total equilibrium. This electric dipole is said to be in total equilibrium. Whereas the same electric field, if the dipole is orienting like this with the minus charge and plus charge. So here F plus F1 positive charge, F1 negative charge is this. Provided they are acting in opposite directions. So net force will be 0. But force into perpendicular distance. Then this is one line of action of one force, this is line of action of another force, perpendicular distance between them. If this is what? L, then L, this will be L cos theta, L sin theta. So force in the perpendicular distance is torque is not equal to 0. In this case, when the dipole is in this orientation, then it is not said to be in total equilibrium. It will be only in translation equilibrium, but rotational equilibrium is not valid here. This kind of questions you have to understand by using the concept of what? Total equilibrium case. Okay? That is briefly about this. That's it. Next, we'll see another very important part of this chapter, moment of inertia. Moment of inertia. Write down. Next subheading, moment of inertia. Moment of inertia. So what is moment of inertia? Moment of inertia, within bracket, write down I, capital I. Moment of inertia, capital I. Moment of inertia, capital I. So in general, in the simplest form, if you have a thread, one end you are holding with your hand, another end if you attach to a body of mass m, and if you are taking this and if you are whirling in a horizontal circular motion or vertical circular motion, so whatever it is considered for simplest case horizontal circular motion. Very rare the force which is keeping the particle in circular motion is called centripetal force. It is equal to mv square by r. mv square by r. Yes or no? Centripetal force. So in this case, if say for example this is the fixed point, this is the thread, and this is the body of mass m, it is in circular motion. Right? For this, what is the axis? This is the one. Axis is this. The line passing the center and perpendicular to the plane of rotation is called axis. About this axis, the mass is rotating like this. Now, the product of mass and the distance of the mass from the axis of rotation should be called as maybe radius of circular path r. Small r or capital R, whatever you can use. Okay, it is r. Then, moment of inertia of this rotating particle, is given by I, single particle, discrete particle we call it as discrete particle. Here we come across again two cases. Moment of inertia of a discrete particle system, continuous mass body system. Discrete particle is given by I is equal to m into r square, square of the distance of the mass from axis of rotation. This is moment of inertia of a single discrete particle. Okay, so from this you can say it is measured by using a unit called unit of mass into unit of what is the distance square. So it has unit of moment of inertia is kg meter square. Kg meter square. What is the unit of SI? Unit of I is kg meter square. Is it clear, everyone? Kg meter square. This is what you call moment of inertia. The moment of inertia, where r is distance of the mass from the axis of rotation. Okay. Yes. Here, for single particle, for single discrete particle, for the system of n particles, it can be expressed as say something like if you have a system, here m1 and a distance of r1 and m2 and a distance of r2 and m3 somewhere here. You have m3, the distance of r3 like m4. A distance of r4, like that n number of masses are there. This entire thing constitutes a system. This entire thing is rotating about this axis. Then, moment of inertia of this entire system of particles is given by, you can write here, I is equal to m1 r1 square plus m2 r2 square plus so on plus mn rn square. That's it. Moment of inertia of n discrete particles. Got it? These particles become more and more. We use sigma summation relation. More and more. The particles become stacked together and closely and it becomes what you call continuous mass distributed system. Then we use a different relation. Okay? This is briefly about what you call moment of inertia of discrete particles. This concept is very important. Based on this, we will get some questions also. Okay. Next, let us see for discrete particle system. For discrete particle systems, we will use usually two theorems to find the moment of inertia of discrete particle systems. One is parallel axis theorem, another one is perpendicular axis theorem. Let us see what are those. What is I can say what is parallel axis theorem, what is perpendicular axis theorem. One is parallel axis, not axis, axis theorem. What is parallel axis theorem? Parallel axis theorem. If you have any system, actually the parallel axis theorem is applicable for two-dimensional bodies or three-dimensional bodies also. But perpendicular axis theorem is applicable for two-dimensional bodies. If you have any body, let us consider one a disc or a ring, a simple case, or any system you can consider for that one. Parallel axis theorem. If this is a point, called center of mass. If you want the moment of inertia of this body about an axis passing through here. Here you have to be careful about the terminology. If the axis is touching the diameter, not passing through diameter, if you have a circle, if the axis is passing through diameter, means it will be lying on the plane around the diameter, any diameter. If it is touching the diameter, means this is the diameter and this is the other diameter. Touching the diameter means it may be here or here. Are you following this? If the axis of rotation is touching the diameter, means it may be this axis. And if it is touching the diameter and lying in the plane, then it will be this. If it is touching the diameter and perpendicular to the plane, then you have to take this line like this, a tangent. Is it clear? Axis touching the diameter means it should be a tangent. And in which plane it is acting, that is also important. It is in the plane of the disc or perpendicular to the plane, that is important. If it is like this, for example, in the plane, or they say in the perpendicular to the plane, let's say like this. This is the axis. If you have a disc, so we are considering a disc, and the axis is passing through, touching the diameter and perpendicular to the plane. Then what is the moment of inertia of this disc about this axis? If you want, you have to say moment of inertia of that about this disc about that axis is equal to moment of inertia of this about an axis passing through the center of mass, and parallel to this axis. Are you following this? So that is ICM plus product of mass of the disc and the distance between the parallel axis. If this is A, then it will be A square. So if the axis is lying in the plane only, then you have to consider moment of inertia of this about its axis passing to the center of mass. Parallel axis you have to consider, that is very important, parallel axis. Then according to this, it is like this. So according to parallel axis theorem, moment of inertia of any body, for a disc or a sphere or anything, or cylinder or for ring, whatever it is about any axis is equal to sum of moment of inertia of an parallel axis passing through center of mass and product of mass and distance between the parallel axis. This is called parallel axis theorem. This is called parallel axis theorem. Whereas the second one is perpendicular axis theorem. Perpendicular axis theorem. As I said, it is applicable for two-dimensional bodies only, like discs or laminas. So if you have a disc, or lamina, and hence this is a disc lying in this plane, and here, if according to this, moment of inertia of this disc about an axis passing through center of mass, this is center of mass about this. Let us say this is you can call it as z axis or y axis or whatever it is equal to sum of the moment of inertia of two mutually perpendicular axes which are concurrent with this axis, means having same origin. can say this is x, y or z axis like this, lying in the same plane. This is x axis, this is y axis, this is z axis, or if you say this is x and y are lying in plane and this is z axis, then write Iz is equal to Ix plus Iy. That means moment of inertia of a lamina about an axis passing through the center of mass and perpendicular to the plane is equal to sum of the moments of inertia of the same disk about two mutually perpendicular axes concurrent with this axis. Concurrent means having same origin with this axis. This is Ix plus Iy. Is it clear, everyone? This is called perpendicular axis theorem. This we'll use in some cases of finding moment of inertia. Okay, these examples to understand afterwards. Let us see briefly the last concept of this. What is the rolling motion? Rolling motion. So what is this rolling motion? Do you have another chart, please? Chart, please. No chart. Right. So next, write down for heading rolling motion. So note on this. Copy parallel axis theorem and perpendicular axis theorem. Then write down rolling motion. Rolling motion. It is also called as a rolling motion. We come across some different cases. Okay. In general, rolling motion is termed as the sum of translational motion plus rotational motion is called rolling motion. So you can write the heading rolling motion. Heading rolling or rolling motion. So rolling motion simply can be called as a rolling. Simple, rolling. That's it. Okay. So rolling motion or rolling is said to be sum of translational motion or translation plus rotation. Translational motion plus rotational motion together will give you rolling motion. What is this? How to understand with the help of a diagram? Let us see. Right? So if you have a block, just let me give you here. If you have a block having some mass here, apply a force here, it will be sliding on the surface, right? This motion is called pure translation, right? Whereas if you have a disc attached here, pivoted with some support, then it will rotate about this fixed axis. It is called rotational motion. You understand? It will just rotate. It will not move anywhere. So here it is just only in translation motion. It is only in rotational motion. Now, if you consider a big wheel or a disc, if you consider a big disc, even if you push this, it is sliding. Then it will be called as, or it is called as a translation motion or linear motion. Whereas if you consider a center point called center of mass, now if you apply a force or push it, so that every particle will be here, every particle will be in what you call circular motion about the center, provided center of mass will be always in linear motion with the velocity of ACM. Is it clear, everyone? So every other particle will be in circular motion. When other particles are in circular motion, and if you draw, say for example, I consider a particle over here on the circumference of this part, this also will be in what? Rotational motion or circular motion in this case. So here, if you draw a tangent to this, it gives the direction of velocity at that point. What do you call it? It gives rotational component, and at the same time it is rotating about this axis, at the same time it is moving forward. So the total velocity here is nothing but rotational velocity. As we know, the relation between linear velocity and rotational velocity, tangential velocity in terms of rotational component is given by V is equal to R omega. So it will give you tangential velocity in terms of R omega plus velocity of center of mass. Together this will move forward. It will be moving forward and at the same time will be rotating and moving forward and rotating. So this kind of motion is called rolling motion. Is it clear, everyone? Whereas here, if you consider a particle, here also if you draw a tangent, we will be having r omega in this direction, but this particle also will be moving forward with the velocity of AC. Based on the point of contact with the surface, components of velocity at this point, you have to define which is under what condition. It is pure rolling motion or impure rolling motion. What is this pure and impure? You understand. If the forward motion of this point of contact is greater than this, then this wheel will slide instead of rotating more. Whereas if the backward force is more, it will not move forward. If it is more, it will slide forward. If it is more, it will slide backward. It is, for example, Asma, girls, the following are getting more boring. Right? Okay. Very good, very good. Right. So because to finish this, you cannot take what do you call relaxation examples. We have no time to take in that way of the session. Okay. So here, if you see in a rainy season, there is mud. The vehicle tires will roll back. It will not move forward. That is the case of this. If the backward force is more than forward, we call it as backward slipping. Backward skidding or backward slipping motion will take place. If this is more, forward skidding will take place. But if velocity of center of mass is equal to r omega, then the body will be under pure rolling. So this is the condition for pure rolling motion. This is the condition for pure rolling motion. Okay? Pure rolling motion. So whenever the body is in pure rolling, so then you can say the total kinetic energy of the body, because it is motion, only kinetic energy to be possessed is equal to translational kinetic energy plus rotational kinetic energy, both will take place. Translational kinetic energy, if a body of mass m is moving in a translational motion, translational kinetic energy is half mv square plus rotational kinetic energy is half I omega square. But omega you can write in terms of v and r also, because omega equal v by r, if substitute, and I, if you substitute with the moment of inertia of that particular body, the disc or sphere, depending on that. If just about this axis, if you substitute the moment of inertia, then you will get this entire term. What you call in terms of v and r also. Okay? So this is about the kinetic energy of, total kinetic energy of the rolling body. It is equal to translational kinetic energy plus rolling kinetic energy. So these are few terms you have to remember about this rolling motion, and this is the condition for, you can write down this. This is the condition for pure rolling motion. Condition for pure rolling motion. This is called condition for pure rolling. Condition for pure rolling. Okay. So keep in mind these few simple points. Okay, and try to work out some questions based on this. Questions will be given. How to find the rotational kinetic energy, translational kinetic energy, total kinetic energy of a body in pure rolling motion. Okay, as a time up already, I would like to wind up this. You guys try to practice few questions as well based on this. Fine? Right, okay. Okay then, so I'm winding up.